Okay, so we are now looking at insulators. Now, insulators are not capable of supporting the flow of electricity. These things have 5 to 8 electrons in them. All right, so let's say you had, I don't know, Pokemon cards, and you had all but one. Would you give somebody one? I don't think you would. And neither will these. So if they have 5 to 8, 8 is full. It has no interest in taking an electron or giving one. If it has 5 to 8, it is going to take one. It's not going to give it. And once it's full, right, nothing leaves it. If it's got 8 in it, then it just totally just sits back and it just lets things happen. If it has 5 to 8, it shows up. It's like that the roach trap, right? The roaches check in, but they don't check out. Electron goes into it, stops, so it doesn't support the flow. It takes it, it keeps it, and it won't give it up. So things that are good insulators: rubber, wood, right? Why do we have telephone poles? Ceramics. If you look up at the power lines, you'll see that they have ceramic components holding the lines. They don't allow electricity to flow through them. Most plastics, not all, but most, and glass. All those original experiments were done in glass because glass, it does not allow electricity to flow through it. Okay, so if you look at wood over on the left here, there's nothing in that outer. I don't know why they show that outer one, but the inner one has 8, so it will not support the flow of electricity. Remember, electricity is the movement of electrons. If it won't move one, it doesn't support it. Semiconductors. All right, now these things are the things that make you go, ugh, I don't want any part of that. But the reality is, this is in the middle, right? So this is 3 or less is a conductor, 5 or more is an insulator. These are 4, right? Dead in the middle, 4. Now, when we have 4, they build like blocks, right? So you get these big matrices, very strong bonds. They don't like to give it up, very strong. So these things are neither a good conductor nor a good insulator. They're right in the middle. Their electrons lock into other electrons. Nobody wants to give it up. And things like this are silicon, germanium, and carbon, right? Carbon. Think about what it takes to clean the carbon out of a car. It's tough stuff. So they have 4 electrons in that valence ring, and they're happy, right? Strong bonds, nothing to share. But mad scientists decided to see what they can do, right? Somebody had to lick a frog to know that they're poisonous or they make you high or something, right? So we go through a process called doping, and it becomes tweaked, right? And it's not the kind of doping that you're thinking of. So we have 2 kinds of doping. We have N-type doping and P-type doping. So if I said to you N-type doping and P-type doping, what do you think is the polarity of N-type doping? You would say negative, I hope. And you're right, right? So N-type doping is negative overall. Well, what are electrons? They're negative. So that must mean that we have an extra electron once we do this N-type doping. And then if I say P-type doping, what do you think the polarity of that is? Positive. Therefore, if electrons are negative, that must be missing one, making it positive. So I'm going to move my face a little bit. All right, so doping means we merged this thing with something else that will give it an extra electron. So we create imperfections by adding arsenic or phosphorus, which gives it an extra electron. And that electron wants to go someplace. So poof, it's a negative charge, and it is a conductor because it has an electron to give. If we do P-type doping, we create imperfections by adding boron or gallium, and that makes it missing an electron, causing a hole, and poof, it's positive, and it's a conductor. It's not a giver of electrons, but it's a taker. Okay? So the things that take advantage of this type of creation are things like diodes and transistors and microprocessors. Those type of things are full of these type of things. You've all bought LEDs, right? You tried to change your lights to LEDs. That is a P type on one side of it and an N type on the other type. That's why when you install a LED in backwards, it doesn't work, because backwards there's no electron on the P side that will flow into the N side. So it doesn't work, right? Not as scary as you thought it was, right? All right, so now we got some definitions. Electricity is the flow of electrons through a conductor, right? So it's the movement of electrons. Electron theory says the flow of electrons, well, let's rephrase that. Electron theory defines the flow of electrons from negative to positive. So electrons are negative, right? If electrons are negative and they're the things that move, then that must be great. The negatives flow from the negative of the battery through the car, through the circuit, back to the positive on the battery. Now we have conventional theory that states that current flows from a positive point to a less positive point. So these two things sound like they are completely opposites of each other, but they're kind of not. All right. So what happens is, if you look up here, we got a bunch of electrons here. And when one electron goes in, it gets near this one, and this one kicks out, and this one goes here, and that one goes there, and this one goes here, and that one goes there, and this one goes here. And as soon as it touches here, then current travels back down to ground. All right? So it took the electrons to flow this way, to touch, to complete the circuit, and have the current race the opposite direction. What did they tell you about lightning? You've always heard that lightning goes from the ground up, right? But we see it come down. We don't see it go up. Well, the electrons leave the surface and float up into the atmosphere. And when they get up into that cloud that's ready to go, as soon as it touches that cloud, boosh, the lightning comes back. And because those electrons are in a pathway, that's why you see lightning strike over and over again, right? 1, 2, 3, 4, 5, 6 sometimes. And you'll see it just trace back that same thing, because that pattern, that road of electrons is still there.